Okay, good evening, everybody, and welcome to our presentation. This is going to be an exciting presentation today about climate change. I'd like to remind everyone that this meeting will be recorded. Did you know there's an increasingly compelling evidence that the world is in overshoot? The cumulative effects of the widely unequal levels of consumption and production of the planet's 8 billion human inhabitants exceed the regenerative capacity of the Earth system. Climate change is a symptom of overshoot. Biodiversity loss and the looming threat of a sixth major extinction is another risk and could be upon us. In this seminar, we'll consider the evidence of overshoot, the economic causes for it, whether green growth offers a viable way out, or if in wealthy countries especially, we must look beyond growth for an escape from overshoot. My name is Chahine. I'd like to welcome all of you today, and I'd like to express my appreciation for all the co-sponsors who have been working hard together to make this event happen. Without your support and collaboration, we cannot go so far. So I want to thank you again, especially the PEO West Toronto chapter, the Toronto-Humber chapter, PEO York chapter, the PEO East Toronto chapter, and of course, Toastmasters Speakers Club of Ryerson Engineering, SCORE, Toastmasters Toronto Engineering Club of Speakers, TECS, and Society of Women Engineers, Ottawa. And of course, our amazing speaker today, Mr. Martin Sears. I want to remind everyone that we have a Q&A session and a networking session at the end of the presentation. If you have questions throughout the presentation, check out the chat right here, and there'll be a link to Slido. Hit that link, you can put your questions there. You can see what other questions are going to be asked, and we'll get to them at the end of the presentation. You can also even vote on which questions you want answered first. Questions will be collected there. And of course, we want to welcome you if you have any questions throughout it, again, through the chat. I'll hand it off to the next presenter. Thank you and welcome.
Hi, welcome everyone, and thanks, Christopher. I'm Cristy from Ottawa, the chair of today's seminar. I'm so excited to welcome you, and we'll learn, share, and discuss our climate challenges and potential solutions to climate change adaptation and mitigation. I would like to start my introduction for the seminar by acknowledging that we are meeting on Aboriginal land that has been inhabited by Indigenous people from the beginning. We want to show our respect for the contributions and recognize the role of treaty, making what is now Ontario. Hundreds of years after first treaties were signed, they are still relevant today. We are grateful for the opportunity to meet here, and we thank all the generations of people who have taken care of this land for thousands of years. Climate change is becoming a significant topic, and we cannot avoid, and we should take action as soon as possible. This seminar is organized under a group of people at the PEO who care about climate change issues and really want to make a difference based on our multidisciplinary background. Our mission is to help engineers, practitioners, academics, decision makers, and regulatory committee members to set a vision and work on action plans, strategies for climate change adaptation and mitigation in Ontario. Now I will pass my torch to Spiros to introduce our guest speaker, Martin Sears.
Thank you very much, Cristy. Good evening, fellow guests. Dr. Martin Sears. He's a postdoctoral fellow at the Institute for Integrated Energy Systems at the Department of Civil Engineering at the University of Victoria. He works at the intersection of energy analysis, macroeconomics, and deep decarbonization studies. He is keenly interested in new approaches to the study of macroeconomics that considers both the physical and financial system dimensions of economic activity, and he actively publishes in this area. His research interest is in the relatively new approach to economics called economic macroeconomics, specifically in the derivation of stock flow consistent input-output models. Dr. Sears holds a master's degree in economics from Carleton University and a PhD from York University in ecological economics. He has previously worked as an applied economist in Cambridge, United Kingdom, on a large-scale model referred to as E3M3, exploring the environmental, societal, and economic impacts of various policy scenarios. And now, I turn our presentation to Dr. Martin Serres.
Great, thank you very much for that introduction, and I'm quite excited to present on this material to you all tonight. So let me just get the presentation up. Can everyone see the screen just to make sure? Perfect. So, as might be somewhat apparent, I am not, in fact, Dr. Peter Victor, nor do I have a fantastic British accent like Peter Victor would. He's had to, cancel the presentation at somewhat last minute due to a health issue. But as his previous PhD student and current postdoc, I'm going to do my very best to present his work in the same spirit he would, and really dig into a bit about the kind of issues and complexities surrounding this notion of overshoot. So Peter is emeritus professor at York University. As was noted, I am at the Institute for Integrated Energy Systems at the University of Victoria. So this presentation is going to follow the following outline. We're first going to spend a fair amount of time thinking about the various and many dimensions of overshoot. We're going to then think about what ecological economics is, and it's kind of very radically different perspective than you might have encountered with basically any other form of economics. We're going to spend a bit of time thinking about the incredibly challenging problem of thinking about the future. We'll move on to climate change and green growth, and in this section we'll think a bit more specifically about emissions reductions and their relationship with economic growth. And finally, we'll end off with a little spiel about green investment and one possible way we might think of escaping from overshoot. And just to be upfront about this, most of the material in this presentation was in fact Peter's. It's based on his book that he's writing, which is called Escape from Overshoot. So again, much of this is his material, and I will do my very best to present it as if I were Peter himself. I'm sure he'd laugh if you could hear me say that. So let's start off with some really, really big picture stuff. Oftentimes, this kind of canonically famous image of the Earth is taken as this kind of really inspiring thing. We finally see where we live in the universe. We gain some new appreciation for how tiny and insignificant we are. That's usually how this is brought up, but I want to use it for a very different reason. We can see right now, this nice little marble in front of us, a planetary scale process, Earth system, atmosphere, what have you. And I want to start by saying that the problems that we face in overshoot exist at this scale, right? We're all familiar with the basics of climate change. Of course, this is a global scale process, but then we have to move down just from climate change. We have species extinction, we have biomass loss, we have all sorts of things like local problems like farm runoff. And so we run the whole gamut. We run from the biggest possible problems at the level of the Earth system all the way down to kind of the hyper-local. And so on the one hand, this is kind of a deeply important image because it locates us, gives us a sense of awe, but on the other hand, well, we can see all of our problems all at once. So it's a good place for starting with perspective. So let's think about overshoot using this kind of somewhat adorable cartoon. Here we see a guy on a bulldozer slowly destroying the natural environment, presumably to clear some more space for cars. We see some industrial agriculture with the cow over there. And we see some ecosystems being slowly pushed off the side of the world as we slowly turn everything into farmlands, into place for transmission and for our ever-encroaching cities. The point of this is overshoot is a lot of problems all at once, and a lot of complex problems that we don't necessarily really understand that well, specifically the impacts of biodiversity loss. And so when we talk about climate change, often it's usually very singular. So we think about emissions, we think about negative emissions, we think about pathways, but it's really quite important for us to start from a position of saying that here's a whole bunch of stuff happening. This is the nature of the problem. And it's not really sufficient just to think about solving one of them in isolation. So let's start our kind of journey on thinking about overshoot with kind of two really big macro scale trends going back to 1750. On the left-hand side, we have global population. As we notice, it increases fairly dramatically after about 1900 and is leveling off in this nice S-shaped curve. Similarly, on the right-hand panel, we have global economic output. kind of our measure of the stuff we do as humans. And notably, it also increases incredibly dramatically after 1950. So the story we're looking at now is one of basically the human enterprise, which is flat for a very, very long time, suddenly exploding in size. And of course, this comes with ramifications. We don't get this without having impacts on our biosphere. So if we want to look at this in a slightly different way, we can start with primary energy consumption. So roughly the same time frame, 1800 to 2019, we see this kind of flat usage of primary energy consumption, which then after 1950 again kind of explodes upward in this almost exponential trend. And so we see the kind of really large-scale deployment of coal, of oil, of gas, and then up at the top we have everything else like nuclear, solar, modern biofuels and renewables. And at the very bottom, we have a pretty constant presence of what they call traditional biomass. From an energetic perspective, since 1950, we have really just dramatically increased the size of what we do. And of course, we all know coal, oil, natural gas, nuclear, solar, wind, and hydro, these things have their own varied kind of idiosyncratic impacts. So when we look at this increasing scale over this time, this comes with serious physical side effects in some sense. It's not hard to imagine the damage, the environmental damage caused in part by having a vastly increased quantity of mining. So let's keep going. Another metric we can use to think about overshoot, something called the ecological footprint. I won't really get into the details of it, but basically it's a clever way of showing how much of the Earth's surface we as humans appropriate for our use. And after about 1970, the total amount of the Earth that we're using has exceeded what might be understood as the Earth's regenerative capacity. And so we have a sense of overshoot here. The only way that's possible is if we start drawing down the stocks that let us, that give us the things we need from nature. And so the really obvious example here is you can fish sustainably. At some point you're fishing and your fish stocks are going to collapse. And so much like that, in a much more complex sense, we are using the Earth, using this method, beyond at some point what it was capable of regenerating across time. And so we kind of have this story of overshoot as we draw down the natural resources that we rely on ever since kind of 1970. And you can see this in a similar way using these Earth overshoot day diagrams. These just basically tell us how far into the year do we estimate that we've exceeded the kind of Earth's capacity for stuff in that year. And as, again, that story of our impacts increasing, that Earth overshoot day happens faster and faster. In any discussion of environmental issues at the global level, we miss out on the kind of deep, truly deep discrepancies that happen with inequality. So for example, looking at the top left panel, we have high-income countries. We don't really need to focus too much on these graphs, but the story here is as follows. People in high-income countries are using about 6 times as much, that's 6.0 GHA, global hectare, of the Earth's resources as people in the low-income countries. And this has only been increasing since the data started in the 60s. This has not really increased for the lowest income countries. So there's a deep discrepancy, a very unfair discrepancy in some sense, between the resource use by the wealthiest people on the planet and the least wealthy. And so it is incumbent on me as the speaker to make this point as forcibly as I can. Many of the environmental problems we have are driven in part by the action of the wealthiest parts of the world, which is by no means the entire planet. Unfortunately, it seems to be the case that many of the impacts that arise from our behavior are unfairly impinged mostly on the least causing of them, and the ones who have the least resources to deal with it. So this, both the story at the global scale of what we're doing, and then the truly deep discrepancies, the inequality, if you dig down just a little bit deeper. But let's keep going. There's more fun ways, and apologies if I'm being a bit bleak, but one talks about this subject for enough years, one has to be just very, very on the nose with it. So we can look again, another story, global materials extraction. Well, not really surprisingly, the fossil energy carriers, which we noted before, have increased. Biomass has increased, and construction materials also have increased dramatically. Again, we see that kind of upwards tilting exponential growth. So in this case, we're just digging vast amounts of stuff up out of the ground, moving it around to put into all our buildings, la-di-da-di-da-da. And it's increasing basically at an increasing rate. You can see this on the left-hand side here, which estimates the growth rates of the various categories. Between 1900 and 1950, it was 1.5% increase per year, then 2.7% increase per year, and finally 3% in the last chunk. And if anyone remembers their exponential growth, these things get big far faster than intuition generally makes us think they will. And again, just a different way of saying this with the materials Sankey diagram, but we can compare again the global materials throughput from 1973 to 2015. And we see basically across all categories just a significant increase. And so to hammer home, again, the point of this story is that our impacts on the biosphere, on the Earth system, across many metrics, are just increasing over time quite substantially. Famously, one that's of course truly critically important is the increasing atmospheric concentration of carbon dioxide, as shown by the kind of famous Keeling curve as derived from the Mauna Loa Observatory. And a sobering fact on this graph, as you can see labeled by A, B, C, D, E, and F, these are the climate conferences we've had over time. So we've had, many years of climate conferences, and underlying all of these things is this almost inexorable increase in atmospheric CO2. Now, this is probably quite familiar to many of you, but it has to hammer home. The efficacy of the things we have been doing up to this point is not necessarily all that notable, at least in this key metric. And so the scale of the challenge that we face is really, at this point, quite severe. But we can keep going a bit because the impacts are still more diverse. So an interesting and a bit horrific metric is the decline in what they say, the abundance of populations of various animals and wildlife. And so unsurprisingly, as we've been clearing the environment and destroying ecosystems, this has declined quite substantially from the beginning of the time period of measurement. Similarly, we see that the overfished and unsustainable fishing has increased again from 74, with a large increase in, I guess, what is maximally sustainable fishing. And perhaps the best, and one of the most interesting ways I've seen to show just the true scale of our impacts is this comic from XKCD, which is a great website, by the way. So this data, I think, is originally from Vaclav Smil, which is shown down below, but it's a comparison of Earth land mammals by weight. So here we see humans in the darker gray squares and our pets and livestock in the light gray squares. What we might consider us and our domestic creatures. How this compares then to all the rest of wildlife, shown here in the green squares. So this should be kind of, appalling isn't necessarily the right word, but this should really be somewhat astounding. When we think of the mass, this is literally by weight, the mass of all those wildlife out there kind of pales in comparison to us and the stuff that we used to support us, let it be cattle, pigs, goats, and our many pet dogs and cats. So again, this, when I first saw this, it was just kind of shocking because we still, at least I do, imagine this big bountiful nature out there. And I have trouble, until I see things like this, rationalizing just how much of an impact we actually have. A more controversial example in 2018 was a paper by some ecologists estimating the decline in insect populations. And some of them they found to be quite substantial. I think 41% set on the graph here. And of course, I'm not an insect ecologist, but insects play a very critical role in ecosystems. And so a catastrophic decline in insects would bode rather poorly for us. Perhaps fortuitously, this is a result that is under some debate. It's not debated that we're reducing these populations. It might just not be by the magnitude represented here. I'm going to keep going. Apologies for the depressing nature of this talk so far, but we also can see that while forests have been expanding, the kind of net deforestation has continued since 1990. So we hear often of massive deforestation in the Amazon. There was kind of a result recently that said that the Amazon has started becoming a CO2 producing area rather than a CO2 sink. Partly because a lot of it is cleared for industrial scale agriculture. To kind of wrap this notion of overshoot up into something, I guess, more digestible in one page, well, let's look at some kind of social trends, again, from 1750. So we have a bunch of stuff on the page here. We have population, we have real GDP, foreign direct investment, primary energy use, urban population, water use. We kind of have a dashboard of metrics of the stuff that we as humans do on planet Earth presented for us. And invariably, though, with some scaling problem on the axes, we have kind of a consistent pattern. We have this acceleration more or less after 1950. The scale of what we do has accelerated dramatically from the 50s, quite dramatically. And this is across numerous indicators. The complement to that previous slide is that the scale of our physical impacts across a wide number of indicators has followed suit. So of course, we see the most obvious one, carbon dioxide, has increased dramatically, but we also have increases from 1950 in things like methane, a more potent greenhouse gas, surface temperature, ocean acidification, kind of the whole 9 yards. And so if we think back to that kind of first slide about us staring at the planet, well, let's do it in a bit of a more abstract sense. So one way that I guess people have come to think about how we can wrap the preceding discussion up into something digestible is something called the planetary boundaries. And this is quite a fascinating way of looking at the problem for those of you who have not seen this before. But a very large group of scientists have basically come up with a list of various Earth system processes that are vital basically to our well-being and the well-being of the rest of nature. And these span things from climate change, what we might understand as global warming due to greenhouse gas, biosphere integrity, which is mostly measured as the decline in species, but land system change, freshwater use, phosphorus and nitrogen cycle perturbations, how much aerosols we're putting in the atmosphere, ozone depletion, and something called novel entities. And one way to think about this is how they've done it as follows. There's a safe operating space for most of these things. So for example, we might look at genetic diversity here and species loss. We see that here, if you can see my mouse, the background rate of species loss is far higher than what they think about as the safe operating space. Some other things like ocean acidification is still kind of within what they've determined is a safe operating space. Nitrogen and phosphorus have exceeded it quite substantially. And for some things, we just don't know. So novel entities being kind of all the chemicals and stuff that we as a society dump out into the environment. We don't really know the long-term impacts, and we don't really know, well, what is a safe amount and what isn't. The point being that this green circle, if you follow this kind of planetary boundaries framework, gives us an indication of where we want to be from a physical Earth system perspective. Some of them we haven't exceeded yet, some of them we've wildly exceeded. But any kind of, I should say, solution or way out of overshoot follows really in getting us into this space somehow. And as we noted, just going back a few slides, sorry about this, we've had many years now of high-level talks without really much indication that we've, well, without a great deal of indication that we're doing that, right? The problem is kind of increasing over time. And from a climatological standpoint, we care about this for the following, well, for one, at least many reasons, but one of the most important following reasons is if we push the Earth system too far, well, it might change into a very different state. So this is often kind of discussed using a tipping points diagram, but we can imagine looking at the page here, we have this ball in this trough. And if I push this ball most of the way up the side of this trough and let it go, well, it's going to roll back down and go back to that kind of stable point. If I push it too far up this hill, well, it's going to roll down the other one to some new stable point. And if I keep pushing it, it's going to even roll out of this trough and go farther. Well, in some sense, this is a little bit like the Earth's climate system, right? It has a very, well, Earth has been around for 4.5 billion years. The climatological history of Earth is fascinating. It has gone from being, as they say, the ice ball state, where it's mostly covered in ice. We've had hothouse Earths where it's been much warmer than present. The thing is that the system is able to flip between these various kind of modes of operation. And right now we are very, very, very rapidly pushing it from kind of the interholocene state to something that's substantially warmer. And we're doing it at a rate that is just dramatically historically unprecedented. And so when we think of, at least from a climate perspective, keeping our emissions down below some level, well, we're trying to make sure that the ball doesn't roll out of this trough that we're kind of used to, right? Because we've lived in a rather stable, pleasant climate since 10,000 years ago, they call the Holocene. And we run a real risk just thinking about climate change of shifting that entirely. So you have to start off with a few grim things. And I won't mince words. The situation, at least, is presented by that data, and other data is pretty dire. And it's unfair to any audience not to really be upfront with that, because it's 2022 now, and talks like this have been happening for some time. Well, if we haven't been making substantial progress on many fronts and things are getting worse, maybe it has something to do with how our society is structured, what our goals are, what we want. We have kind of this narrative you might listen to all the politicians when they get up. We have to grow the economy, we have to jobs, blah, 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 blah. But that's only one way of thinking about the economy. And that comes from a perspective of where we just think about the economy in terms of the things we're used to, and we don't think about its physical dimensions. So it's nice talking to, it's nice talking to a group of engineers, as you are all, or have trained at some point in time in engineering, which is rather more a physical science than economics. So much of this will probably be pretty obvious. But let's take a look at what might be called the ecological economics perspective. Usually when we hear discussions about the economy, we hear about things like GDP, employment, especially now we hear about inflation. And we don't usually hear about things like materials, planetary sources, what have you. So ecological economists start from a totally different place. We start with a picture of the Earth, as shown here, the global ecosystem. We could call it the Earth system if we wanted. And we start from the premise that the economic system, what is labeled here the economic subsystem, is basically an embedded subsystem of the global ecosystem. All the stuff that we are used to hearing about, the things I just mentioned, inflation, unemployment, whatever, take place in this box here. And this box only functions because we take in energy from the system, we spit it out as waste heat, we take in materials, we spit it out as trash, we recycle some of it, but we rely on this continual throughput of materials and energy. This economic subsystem doesn't happen in isolation. It happens as part of the process that belongs to this bigger Earth system. And of course, just for completion, we get nice solar energy coming in, and eventually this is re-released as degraded heat as well. The point being, economics can't violate the laws of physics. We can't do it. So we never really talk about economics in the context of physical laws or kind of physical principles, but it is you can't escape it. When you look at the diagram like this, we have to play by the same rules everything else does. So we're not going to get perpetual motion machines. We're not going to develop any kind of weird thing to let us out of this. And it's high time that we kind of started understanding the economy as this embedded subsystem, because maybe that will give us some indication of how to escape the prior overshoot problem. And indeed, having not thought about the economy like this in the past is maybe part of the reason why we're in the, shall I say, mess that we're in now anyways. And just a different way of kind of showing the previous slide. Sometime in the past, the economy was a small box, and then we had all that incredible acceleration in the stuff we do, and now we have this very large box where the economy and our activities is slowly encroaching on everything else. And probably one of the key ways we need to think about this, and Peter absolutely loves cartoons like this for this reason, is we often have this notion of natural capital, that as we burn through our physical environment, we'll just replace it with man-made objects, person-made objects. But really, there's no real substitute for much of what the natural world gives us. And so the comic here expresses this pretty simply. We might have a single boat with this very lush ocean with lots of things in it. And as we overfish it for a very long time, we kind of deplete that stock of natural resources, these fish. No matter how many more boats we put up there, no matter how fancy the technology gets, it's not really going to matter if that underlying physical necessity isn't taken care of. So we can get very clever with what we do up here with our fishing, but again, it's still reliant on this bit of nature that we've otherwise just depleted over time. Excuse me. So let's now undertake the kind of incredibly complex task of thinking about the future. And as noted, Peter loves cartoons, so we're about to get a whole bunch of them in a row. But these are a bit comical, but they're also illustrating the kind of incredible difficulty we have in imagining a future that basically doesn't look like ours with a few extra gizmos. So the cartoons that are coming, I think, were French artists who imagined what life might look like in the year 2000. And they'll come after this slide, which I'll just go back to because I wasn't paying attention. So here's a cartoon of possible air travel in 2000. The artist was clearly not very careful. This plane thing's wing is about to clip into the platform. The point is that here we have this kind of somewhat absurd old technology, but this is how we'll be getting around. Here we have the usefulness of electricity in agriculture, where the farmer can kind of just sit in a stool and click buttons, and this mechanized combine system will work. So, of course, we use electricity now, which is not necessarily quite in the way pictured here. Perhaps the most interesting is this image of how housework would be done. We've introduced electricity to the home, but we still see that we have kind of the old-fashioned idea of maids with this kind of janky-looking robot that's going to do the jobs. So it's both futuristic and kind of deeply archaic at the same time. Similarly, how warfare would happen, and this illustrates something quite important. Here we have an idea of modern, I guess, combat, and all we've done is taken a boat that might be in the ocean and made it in the sky. So we've made some big technological leap, but we've kind of just replicated our idea of the past anyways. Again, another one of just heating with radium. And finally, one that is both weirdly prescient and incredibly inaccurate is kind of feeding knowledge to children via some somewhat dubious looking technology. So on the one hand, there's some unknown process here by which knowledge is transferred. On the other hand, someone is turning a crank manually. Why do we care about cartoons like this? Why do we care? Because they express the act of trying to imagine the future. And we can get some things kind of right, but also we're kind of stuck in our way of thinking. We often, like I said, replicate how we do things now with a few modern characteristics tacked on. So one of the things Peter does in his book very early on is introduce this idea of the future cone. So we might all imagine we're sitting here at now. And for those of you who have experienced any general relativity, I believe there's something called a light cone. This looks a lot like it, but I don't think the comparison goes that far. But anyways, so here we stand at the present, and we all project our minds into the future, and we think of things that are probable. Some things might be possible, and there's some things that are just ridiculous. And, you know, probable in the future, we'll have lots of solar panels. They'll help us the energy transition. Possible, we'll electrify absolutely everything, minus the few hard to electrify things. And preposterous is things that in our current kind of understanding of the economy and how things work that we just don't even consider. And one of them is more or less, shall I say, the concluding part of this talk. And it's the nature of what we want for and think of where the economy is going itself. So again, we live in a society right now that is quite determined to have economic growth at all costs. It's completely ridiculous that we'd ever assume otherwise. And so we might put it in this preposterous category. But hopefully by the end of this talk, we'll have at least some understanding of why we might want to look at that lever in the first place. Pour myself some water. It's very hot here in Victoria. And my house is quite old. There's no air conditioning, so I'm drinking water continuously. So let's first start off with a pretty simple premise. So the act of imagining the future in our kind of official way of doing it is often reduced to building really big computer and mathematical models for the purpose of simulations, what have you. The canonical example of this is in the IPCC report. We have hundreds of model runs by something called integrated assessment models. And these things give us projection of the economy into the future, the nature of the energy system into the future, and the nature of emissions into the future. And what we try to do with these things is to capture the important parts. But what we kind of end up doing is replicating kind of our rigid thinking. There's other ways of thinking about the future, of course, but these are very important in kind of the policy context. So if you look at the latest, well, the 2018 IPCC, much of our understanding of the future, pseudo understanding of the future, comes from running models like this. The kind of conventional viewpoint that we all operate under now is basically something called green growth, that we're going to keep growing the economy. You might hear Trudeau say this, at least I've heard him say it himself. We're going to keep growing the economy and we're going to solve our problems while we do it. Part of the reason is as we grow our economy, we'll be richer, we'll have more money to do stuff. And presumably as we get richer, we can deploy some of those resources to solve the problem and everything is great. And this kind of logic is inherent when we think of carbon taxes. An excellent policy idea, but often taken to the point of not doing anything else. So I attended a conference recently and someone noted quite up front that oftentimes we imagine a carbon tax, this policy that the government enacts, we think of it as being, we will think if we make it sufficiently high, everything else follows and we can solve most of our problems. But the key here is the assumption that we can keep growing over time while solving almost all of those problems simultaneously. And this is kind of expressed pretty clearly in this graph here. So what we, under this kind of paradigm, hope is that the well-being of people will increase over time, this nice red line. Economic activity as measured by GDP will itself keep on going, but that our total resource use, that kind of physical stuff, interaction we have with the environment, will level off. It won't grow exponentially like everything else will. Put differently, to make a technical point for a second, for every dollar of GDP we have, which is growing exponentially, we need that resource per dollar of GDP to decline. That's our impact decoupling here. So well-being or economic activity, we want to be doing more of the good things while simultaneously using less of resources in the physical environment. So we become, in some sense, become more efficient with these things. And this is really where the story actually can almost start breaking down. From a physical standpoint, we can't get materials and energy for free, especially energy. We can't just do processes, you know, we can run our trains, power our houses. We can't just do that with ever diminishing impacts. But the logic for the future is that as we keep on growing exponentially, things like economic activity, unless we want all the rest of the physical stuff to grow exponentially with it, we have to decouple it. We have to somehow take the economy and make it basically separate from the physical aspect that underpins it, which from the slide before is a sort of inherently dubious prospect. Obviously, the things we depend on come from the Earth system, and we kind of can't really do without those. So to make this continual growth story work, we have to somehow just decouple ourselves from the underlying physical reality. Part of the research I do at ICEVIC, the Institute for Integrated Energy System, is working out the mathematics of this, and it gets pretty goofy pretty quickly. So let's think about this primarily in terms of emissions for a bit. So here's kind of your just basic carbon cycle diagram. We have emissions on the left-hand side from fossil fuel combustion. We have emissions from land use change. Some of this comes back in the biosphere, some of this goes into the ocean. And overall, because less of that is fixed in the climate system than we put up there, we have an increasing concentration in the atmosphere. This is, I mean, basically this is 101 stuff. Unfortunately, we haven't really been reducing our CO2 emissions from fossil fuel use significantly since 1990. So again, going back to that previous slide where we have all the kind of conferences that we've agreed on, well, the impact has been hard to notice in some sense. has to be said, quite obviously, the COVID pandemic had a really significant impact on energy usage, especially just people weren't driving as much, basically. So this accounts for this blip that we see here. But since 1990, we've had this story of fossil fuel use increasing quite substantially in the 2000s, and then kind of reaching and leveling off in a plateau. On the one hand, it's great. We have GDP still going like this, and we kind of have resource use plateauing, which is more or less what we want to see in that story. But this becomes substantially more complicated in the context of emissions. So from a global perspective, we know that atmospheric concentration is increasing. We can see this in the kind of year-over-year atmospheric concentration graphs from Mauna Loa. So 2021 is the red line. It's higher than 2020, which is higher than previous, yada, yada, yada. The increase and decrease here is just reflects the kind of uptake and release of CO2 during the greening of the planet during spring and whatnot. In Canada, we face basically the same situation. So our emissions increased from 1990 a little bit, and then have been relatively flat from 2000 to 2020. And so again, while we have these kind of lofty emissions reductions goals, even with these in place, emissions have more or less flatlined. So why isn't this really worth celebrating? And this, in the context of emissions reductions, is critical. Why is this, you know, we've made some progress, not really as good of news as it might seem? Oftentimes we hear about climate change in the context of how many more emissions we can release by 2050 or 2100. We call this a carbon budget. We can release X number of emissions by 2100 such that we have a chance of keeping global warming below 1.5 degrees or 2 degrees, that kind of deal. So I've done a bit of math in the background, and the actual emissions trajectory that you need, kind of starting yesterday, looks a lot like this blue line here. We need instantaneous, steep, and perpetual emissions reductions into the future, very rapidly and very upfront, to have any hope of keeping cumulative emissions below some budget. Quite obviously, this does not look like the past data series. So not only as our economy is growing, do we have to keep kind of our material use for many of them to stop it from growing continuously, but for things like emissions, we actually have to send those as close to zero as possible. As we notice, sorry to jump around the slides, historically, we haven't really been doing that. And we're in the place now, and you can again look at the kind of more formal IPCC reports where the emissions trajectories that we're looking for in the future have to basically be vertical. And so it's a kind of an almost unprecedented challenge on how we're going to accomplish that. Playing around with the same kind of calculation, you can develop similar trajectories for much more generous remaining carbon budgets. So look at this graph here. I don't really care too much about the numbers, but basically I assumed a carbon budget about 3 or 4 times larger than the one that we usually think about, and we still get these steep emissions trajectories. And this is partly because we've left the problem till very late, that we have to do kind of unprecedented transformative things really quickly right now. So where does growth come into this? Well, let's do a very simple calculation. We have something called an emissions intensity. It's the quantity of emissions, megatons CO2 per dollar of GDP. And we have GDP. And so if you look at this nice equation here, GHG emissions is just your emissions per dollar of GDP times the magnitude of your GDP. Put differently, if you grow your GDP without decreasing your emissions intensity, you're going to have more emissions. The faster the rate of GDP growth, the faster you need this emissions intensity to decline. So this follows just basically from simple arithmetic. And this is where we start kind of questioning that story we have from before. Reducing emissions per dollar of GDP seems like a pretty abstract thing, but this encompasses technological change, this encompasses the energy transition, this encompasses a whole lot of really difficult challenges. The faster we grow GDP, the faster we have to reduce emissions per unit of GDP. So when we sit here and we say we just need to grow faster to solve our problems, we in fact on some level make it harder. The faster we grow, the faster and more difficult this challenge becomes. And this number is not minor. Going back to this graph, the rate of emissions intensity decline necessary to make this calculation work is something like 8.5%. For even the most generous carbon budgets here, the one that's about 3 times as large, that number is about 5% emissions intensity decline. Historically, we get nowhere close to these numbers except in the United Kingdom, where emissions intensity, it's a bit hard to see, this percent change in carbon intensity year over year is about -5%. That -5% corresponds to something that is way larger than the amount of emissions we have left. Globally, it's about 2% reduction per year. So to make this story happen, we need rates of emissions intensity decline that we've never seen sustained perpetually into the future. And the faster we grow, the larger that needs to be. So the nature of the problem might be becoming just a bit, hopefully a bit obvious at this point. The thing which we kind of, the royal we, not necessarily us here, but kind of as a society, the thing that we kind of unquestioningly cherish and desire as a policy outcome, this GDP growth, is on some level kind of obviously making the problem harder. If we have GDP growth of 3% per annum, in 100 years, that's about, if I get my math right, 20 times larger. That's a really kind of dramatic indication of the nature of the problem. And so an interesting slide that Peter put together is how many countries ever have had this kind of 8.5 or in this case 9.7% intensity decline for even 3 years. And there's just a few of them. And the most consecutive years we've ever seen is 6. So I've kind of already talked about this. We'll skip this slide, but kind of the latest estimate for how much carbon of our carbon budget, our remaining carbon budget we have is about 420 for a 50% chance of staying below 1.5 degrees. There's lots of good reasons why we want to stay below 1.5, but to reiterate, this is not a big number. It's not a big number at all. It gets more forgiving if we get up to 1.7 and 2 degrees, but as the IPCC produced in 2018, there's a lot of good reasons to stay below 1.5. Just watching the time, make sure I don't go way over. Now, in terms of how we accomplish reducing our emissions, there's kind of a few narratives. So let's look at this graph here. We see 3 emissions trajectories. The red is just linear. We reduce emissions linearly over time. Green is a constant percentage decline, basically an exponential decay. And the black one is most interestingly a technological breakthrough. Our emissions are kind of flat like they are now. Some miracle technology occurs and we rapidly reduce emissions and then they keep declining afterwards. Well, from the context of a carbon budget, all that matters is cumulative emissions, right? So for those of you who remember your calculus, it's the area under the curve that matters, not necessarily the curve. So what happens when we take the cumulative of these emissions trajectories? Well, our technological breakthrough scenario blows past the carbon budget, and so does our linear one. The only one that really works is kind of this constant percentage-wise decrease. We always have to think of emissions reductions from the perspective of the cumulative emissions. So no matter how clever we are, how significant our technological breakthrough is that we can reduce emissions kind of overnight, the longer we wait to do that in the future, the more we've blown through our remaining carbon budget. This kind of technological breakthrough would work in some sense if it happened today. So if we all wake up tomorrow and we have cold fusion or just fusion, maybe that might work. But we can't necessarily rely from a cumulative emissions perspective on some just future innovation that'll come rescue us. And I'll have more to say on that at the end of the presentation. We care, I mean, from a very limited perspective in economics, we think about climate change in part for how climate change will feed back in and affect us on in our day-to-day lives, how it will impact economies. And we don't, quite honestly, have a good way of doing it. So this is from the En-ROADS simulator, and it's something called climate damage functions, which are more or less people's best guesses, some empirically derived best guesses at how much of our GDP, how much of our economic output might get decreased as the temperature increases. And what we see is these vary widely. We have the famous Nordhaus one where you can kind of crank up the global temperature really as high as you want. There's not that much impact, which is comparable with the Dietz and Stern, which at 5 degrees global warming, basically civilization has ended. So in economics, we span from nothing will happen to we won't have civilization, all in the same graph. So we're not necessarily super aware or have a great deal of understanding of how this is actually going to unfold. But good people at the Financial Accountability Office of Ontario have done some really excellent work on trying to do more granular estimates. So under medium emissions and high emission scenario, they kind of have done infrastructure cost calculations going out to 2100. And we see these are significant. Billions of dollars for Ontario to kind of manage their owned assets. And the point being, the high emissions scenario is quite a bit more expensive, 116 billion to 66, but also that the range of uncertainty on costs gets pretty dramatic. So basically, we don't really have a very firm knowledge of how this is going to reflect back on us. We know that we'll face in the future adaptation costs. We don't really know what their magnitude is, and they might be very, very high, giving us, in some sense, impetus to reduce emissions before we have to see how that ends up. The point being is if we look into the future, we might be faced with all these climate adaptation costs, climate damages. We all know from kind of the news that we see increasing severity of storm events, flooding. You have really significant agricultural disruptions happening. You have droughts. So these things are in the future almost no matter what. To the extent of how severe they are, that's a different question. But some people have begun to think that these might just slow down economic growth anyways. So there's a variety of perspectives on why economic growth might slow. Because remember previously, faster your economy grows, the harder that intensity decline problem becomes. But there's a bunch of reasons to think it might be sort of slowing anyways. So for example, Robert Gordon has looked at everything ranging from demography to debt, inequality, energy, and a group called biophysical economists have looked at this from a more kind of purely energetic perspective. But there's increasing interest in just whether we can actually maintain growth, even if we want to. And as a reminder, maintaining something at 2 or 3% GDP growth of 2 or 3% per year, that's exponential growth. So it's a pretty tall order. If we look at the data on economic growth itself, well, it's kind of been mostly decreasing with a slight uptick. So the annual growth rate was quite a bit higher in 1960, and it's been basically decreasing mostly over time. If we differentiate it by kind of income type, well, high income countries, the growth rate has just been declining across time for the entire data availability. To account for the uptick in the previous graph, middle income countries have seen high growth rates decrease slightly and increase again, and the low income countries have seen really staggering increase in economic growth, which is leveling off itself. The point being is that economic growth might be kind of hard to maintain anyways. And the biophysical economists, just I forgot to mention this, have their own reason to think this, but moving from things like old oil fields where you could kick the ground and oil would come out to very hard to extract oil from shale and quite other energetic intensive processes may slow growth of its own accord. But if people are curious, I can talk more about that in the Q&A. Other trends that we see now is kind of a leveling off in population. I'll skip these slides on technology for the moment and kind of get to the final few slides here. So just to reiterate a point, just to make sure it's not too confusing, the faster we grow, the harder emissions intensity declines become, the harder it is to reduce our emissions. There's evidence that growth is struggling anyways, be it from energetic reasons or various demographic inequality, what have you. And so we kind of start begging the question of why are we struggling so hard to achieve it? It makes the environmental and physical problems harder, and there's kind of tailwinds against it anyways. So I'll come back to these slides in a moment. Where Peter's work comes in, and what he's quite famous for, is for turning the question on its head and more or less asking, what if we stop growing? Why do we need to grow? We have this kind of unquestioned societal assumption that we continuously need to grow at this exponential rate. And we know that it's at least partly to mostly responsible for many of the problems we face. So what if we thought about the future not dependent on that assumption? We can't control the physical aspects of the world. In some sense, the only thing we have to control is ourselves. So why do we need a society that's perpetually growing over time? And so something that Peter has become, well, as I said, quite famous for is working out the macroeconomics and the various complexities of an economy that doesn't actually need to grow. I'll do it this way. So to kind of cap off this talk, I'm going to look at two scenarios that he's developed to show a way to sort of escape some dimensions of overshoot by controlling the thing that we can control, which is, GDP growth and what we do. So he has two scenarios. One of them is we just continue what we do going into the future, continuation of current policies, trends, and relationships, and an escape scenario, which is some of the things we're familiar with, like an increased carbon price, rapid electrification of road, rail, and transportation, a switch from brown to green investment, which I'll get into in a moment, and other good things like increased transfer payments and circular economy initiatives, and a lower rate of population growth. But the story really to make this possible kind of comes from, sorry, I'm going backwards in my slides, from investment. Investment looking forward is basically key to everything. And this is also in the work that I do. The kind of investment choices that we make today as a society or in the near future really kind of substantially impact where we go forward. So as Peter says here in a slide, investment is the bridge to the future. So let's think about what types of investments we might actually look for going forward. So somewhat ingenious diagram that Peter has come up with is the so-called 4 categories of green investment. We have additional investment, or we have additional and productive. Additional means we invest more. So we have investment expenditures in the economy. Additional is we add on to that. Productive is we add to the kind of productive capacity of the economy. The best way to think about this is we invest in a new factory for producing stuff. We might also have additional, which is we increase our investment expenditures, and non-productive green investment. Something non-productive might be like building a seawall, right? We spend a whole bunch of resources to build a seawall to keep water back, but this seawall itself doesn't necessarily produce new stuff for us over time. We also might have non-additional productive green investment, which is we divert some of our currently existing investment to green technology. And this might be something like electrification, manufacturing, but we divert some of our currently existing investment to green productive technology that lets us build more stuff in the future. And the final interesting category is this non-additional, non-productive investment, which is we divert some of our existing investment in productive capacity to things like seawalls. That is, we take some of the stuff we'd invest to kind of keep building more factories, and we put that into kind of inert things like seawalls that don't give us more productive capacity. So I kind of could have just shown you all of this as I'm doing it. But Peter makes the interesting realization that this kind of non-additional, non-productive green investment might act to reduce GDP in its own accord. We divert investment away from things like new factories to produce stuff, and we invested in things like seawalls, which don't give us stuff going forward. This is kind of a critically important dynamic when we think about the future of growth, because a lot of what we might have to end up doing is this non-productive, non-additional investment. Thinking solely about sea level rise, if we have to start making kind of massive landscape changes to protect ourselves, that's a lot of what we do, a lot of our productive activity going into something that doesn't really keep or doesn't give us new productive activity going forward. And so Peter just gives a few examples here. Some of them are quite interesting. These things give us kind of net benefits, but they're financially not so beneficial. So we might think of land restoration, carbon capture and storage is incredibly expensive, electricity storage as well. They're necessary and they give us a bonus. They don't necessarily give us a good financial return. And kind of overall, as we shift from brown investment in productive capacity, as we shift green investment into green investment into things like seawalls, electrification, we might cause that an additional slowdown in GDP anyways. So it's a bit confusing, but that's part what underlies the kind of scenarios that Peter has built. So again, we have this base case where we just continue what we do into the future, continue current trends, and this escape scenario where we kind of redirect our society to stuff that might not be productive, might not give us financial returns, but it achieves some of the kind of environmental objectives we might have. And so, because we're economists and because we do modeling, we get lots of confusing graphs out of this. But this gives us an example of a few metrics and how Peter's very complex and very fascinating macroeconomic model sees the future. In the top left panel, we have materials flows. We have a base case scenario, current trends, and an escape scenario. Under the specifications of his escape scenario, the material flow requirements decrease quite substantially. The base case is flat, like we've seen at least for emissions. For greenhouse gas emissions, again, we see declines in both, but really substantial declines in this escape scenario. And this kind of holds true as well for ecological footprint. The cost for achieving this, if I may say it as a cost, is that GDP growth basically grinds to a halt in the escape scenario. Combination of things like work time reductions, combination of things like shifting our investment from productive brown assets, which are possibly environmentally destructive, to that green investment that isn't necessarily productive, conspire to basically stop GDP growth in this scenario. If we remember going back to the future cone, this is still kind of something viewed as conventionally as preposterous. It's been, increasing in popularity lately with, for example, Greta Thunberg talking about this at rallies. But this is ultimately a vision of the future that looks very different than what we kind of expect to see. And so I want to kind of end off this talk with what I think is very important, which is the role of imagination, which might sound a bit weird as an engineering talk. But this is at least to me quite critical. So let's think about this. We have relatively good understanding of the technology we need for a transition, right? I'm not an engineer, I'm not a power systems engineer, but technology exists to integrate renewables into the grid, hopefully in large numbers. I don't think there's anything fundamentally complicated, or well, fundamentally we don't know. We are less well informed about things like negative emissions and geoengineering, those kind of more radical solutions we have to our problem. But escaping overshoot might require more than just a better understanding of the physical problem. In Peter's work, he's shown that it's possible, at least in one way, to escape overshoot by changing our assumptions about what we want for the future. Again, of the things that we do control, what we do as a society, we can achieve substantial benefits to our environmental problems by assuming away the growth in GDP, assuming away that growth in the scale of things that we do. Many of the first slides, and the reason why they're here and why I showed them, shows that as we've been accelerating in the things we do, our GDP and other various indicators, that problem has accelerated with it. And it's taken a very long time for people to kind of come to the ingenious understanding that maybe the thing that has to give is the GDP growth in the first place. The role of imagination, why I think it's critical, is because this is very complicated. We don't really know what that looks like going forward. In Peter's scenarios, he assumes various things to make this situation plausible, partly amounting to redistributing income, to lowering work hours. The point being is that we're looking into a very different future when we think about this. The problem is that there's not really any evidence that the more conventional way is actually working. So given the severity, the incredible complexity, and shall I say diminishing time we have to solve the nightmare problem I started this talk on, we need to kind of expand our sense of the future. We need to be more open to different perspectives on how we go forward. And so kind of one of Peter's ways of escaping overshoot is to redirect our idea of how we think about the economy in the first place, and to assume it doesn't need to kind of just grow forever into the future. And maybe to find a way that that might be beneficial for us without bringing everything down with us. But again, this requires a work of imagination and a lot of hard work by, in some sense, more than just engineers. We look forward, we see a significant problem, and we kind of have to build a society that'll, hopefully get us out of this. And that might require deeply unconventional thinking. Anyways, I hope I haven't gone on for too long. Thank you for listening. And I'm happy to answer any questions about anything that wasn't clear. But I'd just like to say thank you very much to the organizers for having me.
Thank you very much, Dr. Martin Serres. Great presentation, and I really, really love the comments. We've collected some questions and comments on Slido. I will go through the top 3 questions with you so that we can keep the seminar on schedule. But I'd like to just remind everyone that we have a Q&A and networking session at the end of the seminar where we'll keep answering the rest of the questions on Slido. So if you'd like to ask questions and network, there'll be opportunities at the end. So the top question is that, can we have a copy of this wonderfully put together slides with stunning information?
So
it's got four thumbs up.
The answer is, I think yes. I'll have to ask Peter because most of this is his work, but I'm pretty sure he's fine to hand out the very beautiful slides.
Okay, perfect.
Yes, definitely.
Awesome.
That was an easy question.
Yeah. Maybe we'll add one more. The second one is, how do you suggest governments can be convinced to make the difficult decisions required in time?
I think if I could answer that truthfully, I would be very quickly given a Nobel Prize. Honestly, from my perspective, Peter might have a more nuanced answer than this. I don't know. It's not necessarily the most helpful answer, but there's a certain inertia in how governments works, such that even slightly radical ideas take a certain amount of time to boil through. So as I noted midway through the presentation, I was at a conference recently, and some of the presentations were from people at government departments, and it just takes ages and ages for ideas to percolate through. We tend to think that we can, elect something brand new and that will make change overnight, but a lot of these policies are really complex and we don't really have a good understanding. So even getting the carbon tax was kind of a Herculean effort. So in reality, I actually don't know. That's a fantastic question, but I do not know how we can make the move at the rate that seems to be suggested.
That's a great answer. Then we'll probably pass the question to Dr. Peter Victor to see what he thinks. Maybe we'll populate the answers from him to the audience. The next one would be, can you comment on how you see the role of government and the finance industry in helping to change the behavior needed to move towards net zero or sub-net zero, or sub-zero, sorry.
Well, that's a really interesting question. In some sense, we have this notion that really long-term risky things probably are better handled by the government that tends not to collapse when their subprime mortgages go down. The government has, in my very idiosyncratic view, it needs to lead on basically everything, right? For example, and I'll give a very specific example of this, in the States, when you try and set up new grids, when you try and introduce renewables to grids, you get this kind of unholy sea of red tape. So I want to build a bunch of wind turbines somewhere. They're going to be in state here. Transmissions are going to cross state lines. The grid is not able to necessarily incorporate these things. This takes time. There's laws in the way. There's conflicting laws in the way. So in some sense, the government needs to, at least in the States, at least for this example, really get its act together to making things, the basic necessities of the energy transition, a lot easier. In terms of finance, this is a very interesting question and something I work on myself. If you need to transition your energy system basically, not overnight, but basically overnight, you need a whole lot of finance to come from somewhere. I'm not aware of how easy it is to get private finance to just provide that at the rate it's needed. So in some sense, the government might literally have to step in and do some of this itself. I don't know how feasible that is. I'm not an expert on tax policy, But because, again, the government is the thing that we elect people and they can sort of do stuff, we might rely on their kind of more executive power to do it. It's not a great answer to your question because, again, I just don't know. But given the time frame and given the kind of legal complexity, I think they could do that. I see a comment. It's not easy to get financing to do the right thing. Amen to that. It's non-trivial.
Do we have time for the fourth question? It would be a quick one, I guess. Given the observed political influence of COVID deniers, what is the likelihood that we can overcome the political influence of climate change deniers? I guess I misspoke. It's not going to be a quick answer. But.
Yeah, you guys are all asking really easy questions. So I forgot to mention this during the presentation, but one of the slides I wanted to add was, aside from overshoot and environmental things, I'm getting a sense that we have a disastrous increase in misinformation, making things ever more difficult to govern. You see this more in the States than in Canada, but this kind of ability for nonsense to spread its tendrils absolutely everywhere and make long-term solid policymaking happen seems to be incredible. So the general rise in conspiratorial thinking, the general rise in misinformation, that's really quite tough. It's more or less the same dynamic at play. Can we get through that? I'm not sure. That's a sociological question. Something has gone somehow terribly wrong in our social fabric to have lots of society turn to these things. And answering that question requires figuring out why that's happening and how we can address it.
Great. I've seen like flood of questions coming in, but I will save those questions at the end of our seminar. We'll have a Q&A session coming up at the end. So I'll see you there. I'll pass this to Mikayas.
Hello, everyone. My name is Mikayas Kurara. On behalf of PEO's Climate Group, which is the main host of this webinar, I would like to thank our today's speaker, Dr. Martin Sears, for the informative presentation. We all learned a lot from your presentation. Thank you for your time. Thank you all the participants who attended on this webinar. Next, I would like to thank our co-sponsors, the PEO Humber chapter, York chapter, Ottawa chapter, East Toronto chapter, PEO Peterborough, Institute of Electrical and Electronics Engineers, Peterborough chapter, Toastmasters Speaker Club of Ryerson Engineering, SCORE, Toastmaster Toronto Engineering Club of Speakers, TECS. These were our co-sponsors. Thank you, everyone. And next, I would like to pass for the next speaker, Luis. Thank you, everyone.
Thank you, Mikayas. Thank you, Dr. Martin, for a great presentation today. In the climate change group that we are part, we are discussing during all these months about how engineers we can mitigate the effects of climate change. But I think that today you show us that is more that engineering work. I think that we could see on your presentation the effects of population on the planet, how the population consumes resources, and how this is going out of control. And I'm really got surprised when you saw the picture with the fishing ships, that doesn't matter the technology that we use, that if we finish the resources, doesn't matter the technology that we have, that we can't do anything. Then I think that today with your presentation, the conclusions that we can get is that we need to do much more that we are doing, not only as engineers, I think that also as citizens. I think that we need to change our consumption habits in the way that we can help to avoid this way of growing. And about investments, I think that one of the keys was that we also need to think how we invest, in the way that we invest, because not only thinking in the revenue of the investments maybe is the way. Then thank you very much for your speech today. I think that it was so informative. I think that it was so relevant for all the group. We had around 100 participants during the meeting. I think that is great. And every month we will keep working on how we can mitigate and how we can help with climate change. Anyone that wants to join this group is invited to join it. Just write on the chat or get in contact with Jim Chisholm. And also we have our YouTube channel. Also you can follow the YouTube channel. Thank you very much for the presentation again. And I'm going to the next participant that I think that we are going for a Q and answers session, but outside of the seminar. I don't know if Jim wants to close the seminar officially. I will add the spotlight and we can close it.
Okay, just very briefly, again, thanks very much, Martin. It was just an excellent talk. This was the 11th seminar that the ad hoc climate change group, mostly of PEO members and a few other supporters of the engineering community, have put on through the PEO chapters primarily. And it's with the purpose of putting climate change more on the radar of the PEO. I mean, you made reference that sometimes it's hard to percolate issues down and get changes. And the PEO is a great regulator, but from my perspective, it could be doing a much better job in advocating for the public interest, and in particular advocating for climate change. We have the regulator in BC that's been at this for 10 years, has a fantastic action plan. So hopefully our 11 seminars and this one today has helped again put the whole issue of climate change more on the agenda of the PEO. And hopefully at some point the PEO will take the next big step forward and say, yes, we do have to start advocating for the public interest as it relates to climate change and develop an action plan on it. So thank you for, again, a great seminar today, and thank you to all the volunteers that helped make it possible. So at this point, I'd like to adjourn the meeting, but as indicated, there will be a question and networking session that will start immediately. And Kemi, I do believe you're going to lead it off. So back to Kemi.
All right, thank you, Jim. Okay, so Martin, are you ready for the floods of questions? Just in the last 10 minutes, I can see people's enthusiasm coming at us, as I've seen like 10 more questions coming up. Yeah, let's get them.
All right, I'll do my best. One runs out of glucose after talking for that long, so expect.
So the first question would be, in the escape scenario, will people's basic needs still be met if material flows decline so sharply? Or does it assume that a significant decline in population?
So specifically in population growth, it assumes a lower rate. So basically population projections, I think, just stabilize anyways. So this just assumes, I think, I have to be more careful with Peter on this one, a faster rate of stabilization. So it doesn't include anything really nasty and dramatic. So the escape scenario is predicated on more or less delivering stuff that we think is good without necessarily causing a disaster. And this follows from Peter's book, God, like 10 or 11 years ago now, which is Slower by Design, Not Disaster. So no, to the best of my knowledge, the escape scenario is not really an apocalyptic one, but it does involve things like work time reductions. And that does involve things like, you know, in some sense, a decline in the wages you might receive. So you don't get things for free, but it's not an apocalypse, to be sure.
But does it also mean that you would like grow stuff in a more efficient way so that it is more sustainable? Because I think about vertical farm. Sorry, I thought about vertical farming, that you can grow plants in the concentrated area so that it doesn't consume much of the farmland. So what's your? Sorry, I just added my question here.
No. So let me, given this is a group of engineers, I'll put it this way. We desperately need the ingenuity of engineers to give us those efficiency gains. Those efficiency gains alone won't just give us to a future where we can do everything, but we absolutely are reliant on them. In my own work, increases in energy efficiency, for example, from a variety of things are the only way I can make similar escape scenarios. So we desperately need those things. We can't rely on them to deliver everything. If that makes sense.
Great, thank you. Moving on to the next question. I think we're doomed. The prime directive of all political systems is to maintain power, so radical changes will not be made until it is too late.
I really appreciate whoever wrote this, because there's a chance for me to ramble, and it's also an interesting thing. So we run into, God, how do I put this? Apologies everyone who stuck around to listen to me say this. We run into the limits of our understanding when we hit questions like that. It is conceivable that we could construct a society, we could imagine a sociology in which we're not playing by those rules, right? So in some sense, that prime directive is, again, a product of our kind of way of thinking. The schools of thought, well, there's two of them. I can think of my lab mate in IceFic, who notes that some of the things we might have to do, some things might take something drastic to happen before we move on them. But I think, and this is my point about imagination, there's many ills in society today, right? This is not exactly a utopia. And so when faced with a future that is quite grim, that requires us to change quite dramatically, it's also quite hopeful because it gives us the impetus and the chance to build something better, right? As cheesy as that might sound, here is a time that we can reinvent ourselves in a way that might be, more equitable, more fair. We might enjoy lives more than the current kind of, shall we say, onrush to disaster. We have to do that. That's hard work. I certainly don't have the answer to that, but it's not necessarily doom. It could be an opportunity.
But doesn't kill you make you stronger?
It doesn't harm you enough so that you can still do things.
Well, thank you for that. Here's another comment. It is not a question, but I believe novel entities on the planetary boundary slide has recently been quantified, and it's exceeded its limits. It's just a comment from the audience.
No, that's great. I actually forgot, but you're right. There's a recent paper out by a group that I can't remember who did that. And you're right, that would have made the presentation even more grim than it was. But thank you for reminding me.
Back to the previous question. We're doomed, I think. All right, moving on. Are there any decent data on increase in infrastructure costs we already see due to climate change? For example, all the recent floods, likely more persuasive than forecasting.
Yeah, so the best data that I can think of right now actually is the FAO report I shared. They do, from my understanding of the report, a really intense inventory of all the structures owned by the provincial government in Ontario, and they make assessments across several different types of physical risk, and then they project the, I think, additional costs to manage those things. So that, see if I can share the link somehow later. But that's like the gold standard from my understanding of trying to figure out those additional climate costs. When you move to a bigger scale, when we don't think of just specifics about a building, then they just become, a little bit sketchier to say. When we think about costs at the level of an entire economy, at that point, it often is just guesswork, to be completely honest. And as shown with that graph of the different kind of climate damage functions, we run the gamut from the end of existence to nothing will happen. So my best guess on that front, and this is just me speaking in my best guess capacity, is we're underestimating, at least on that scale, quite significantly the damages.
Absolutely. Is it possible that when you find the link, you can send it to us?
Yeah, yes, I might be able to do it right now, actually. Sorry, please bear with me while I do this in the background.
Can you do multitasking? Because we have.
I can
more
certainly
questions.
try.
Sorry,
Yep.
I'm kidding.
Hammer me with questions. I'll try and do both.
This one is from Don Clayhorn. Sorry if I pronounced your name wrong. You can, if you want to speak up, I see that you are here. If you want to open your mic and just ask a question to Dr. Martin Sayers. But if not, I can definitely ask a question for you.
So you required me to find my mute button. Is that, can you hear me?
Yes.
Okay, yeah, so thanks for asking me. I guess it dawned on me toward the end of the presentation, it seemed you were saying Peter was asking, why do we need to grow? But it seemed more like he's saying that in order to survive, the necessary actions to take will by consequence stop growth. And maybe it's just saying the same thing, but it's not saying let's stop growing, it's saying let's do the right things so we survive. And as an outcome, based on the modeling you showed, that will essentially nearly stop growth.
So this is a brilliant point. I want to thank you for raising it. So this comes in two parts. There is our kind of normative judgment that maybe we should stop growth because of the host of problems that comes with it. And there is, so we might do that for our own reasons. We might see the problem. We might say, all right, let us rebuild society, let's stop growth as society. That's something we choose to do. On the other hand, there is evidence, I don't know how, if we know for certain, that doing those policies might make that happen. But there's a difference there in that one is the thing we might choose to do, one is the thing that could actually just occur as a consequence. I am not aware, I don't think really anyone is aware that if we do those policies, that would be the impact. There's evidence, as we saw, that growth is slowing anyways. Those policies could make it slow even further. But again, one is something that we choose to do, one is a possible impact that could occur. Hopefully that clarifies it.
Yeah, that's good, thank you.
Perfect. Let's move on to next question. Can you speak the role of engineering and engineers in Overshoot and what we need to do differently in the future?
So I'm trained in math and then economics, but I find myself in an engineering department right now. And this is going to sound like a bit of a weird answer. So I'm not an engineer, so take this with as many grains of salt as you want. But there are specific complex engineering problems we still have, right? I don't know. So I have some colleagues, for example, in power systems engineering. That's a viciously complicated subset of engineering, electrical engineering, I think it's actually called. Do we have a good understanding of what it means to run a society with enormous amounts of variable renewables, right? So there's basic physical problems that I think we still have. So the role of the engineer in some sense is still the role of the engineer. You guys have some desperately hard physical problems to work out. I guess on the other hand, engineers, at least in my experience, also play nice with economists when they build these kind of models of the future. And the engineers are often brought in to do things like to build the model's power sector, to build the model's XYZ materials sector. At least in my very specific circumstances, the role of engineers might be to look at the economists across the table. And when the economist says something that violates basic physical reality, to say, well, that doesn't make sense. So we have a lot of models in the IPCC reports. They like to spit out really long trajectories. There's lots of physically dubious things happening in there that the econ people, like myself, don't have the training to really analyze. But yeah, I mean, the role of engineer to me is just, we got problems that we still don't really know how to handle. So I guess you guys have to solve those too. And going forward, I mean, even more, if we have to start doing kind of really large scale infrastructure repairs, developments, I mean, think about it this way, right? The suite of things that might happen under a fairly large amount of warming requires us to basically reconstruct our built assets in ways that don't just kind of degrade immediately. So those are challenges that I really have no bearing on, but I mean, the engineers have more and more to do in these dire scenarios. I'll stop my ramble with that.
Great, thank you. The next one would be, what do you think the best way to achieve the significant changes required in a democratic society with rights and misinformation dominated the discussion?
Again, these are really good questions. That's a really tough one. I think the best chance we have is to see an example of something functional somewhere. So if we look at the morass that is the United States right now, not really the most functional, probably don't have a great deal of hope that they're going to do overly sane things often and always. But I think the best chance we have in a democracy where people are reliant on information to make choices is to find somewhere on Earth that does it really well. That's a kind of shining example on the hill. I mean, the misinformation problem is hideous. Honestly, I mean, some of you probably live in Ottawa. It happens. This kind of influx of misinformation that leads us to wasting tons of political effort on, things that don't matter. I don't know how to get around that. I honestly don't. But I think, much like we see with the kind of children's campaign led by Greta Thunberg, the power of an example is really significant. So if there exists a country, probably in Scandinavia somewhere, that manages to do a lot of the things that we need, then we can learn from them. One has to hope that that helps combat that misinformation.
Thank you very much. Moving on, this is going to sound very negative. This is from the question. But to preserve all the other species, maybe it would be best if the human race ceases to exist, and the sooner the better.
Oh,
I think that's a comment. Yeah.
Well, I have a really, again, cheesy answer to that comment.
Yeah.
So some of you might be aware of the Fermi paradox, where we stare out into the heavens and we find no sentient life staring back at us, right? So, I mean, from that perspective, the universe doesn't generate, sentient things that do things like make poetry that often. So we should prize ourselves a little bit more than just that. Any solution going forward, obviously, I hope won't be that radical, but we're valuable too, right? We just have to find a way to, in some sense, coexist.
But have we yet passed a great filter?
We got sci-fi real quickly.
Moving on, next one. Do we know the seafood situation really is, especially as fish farming has not been the success it was expected to be? It's from William Good. I'm just trying to find it easier. Sorry.
I think the seafood situation is pretty dire. From my memory of reading about it, there's much like other bits of biodiversity, we're doing bad things to the seafood situation. So I don't know the specifics of how environmentally friendly factory farming fish is, but the state of biodiversity loss in the oceans, I think, is pretty grim, and that's magnified by the acidification problem. So yeah, there's things to be worried about there for sure. To the extent that kind of synthetic fish farming can take over, I'm not certain.
Great, thank you. There's one more question. Are there any examples where a society has ever moved to more equity? Almost always the opposite is true, concentration of wealth. How can this be changed?
I'm gonna about 5 more PhDs. I'll give an intriguing example that might sound quite roundabout, but I read something really fascinating a few years ago, which was kind of looking into deep history for what might be called very sustainable societies in the long term. And so I think it was Balinese islanders had this completely different setup than we have. And they kind of manage their natural resources through a sequence of local religions, rituals, and their own hierarchies. So there's examples in the past of civilizations, peoples, groups that look very different from the one we have, that show a great deal more promise to kind of environmental management. Given the kind of semi-permanent increase in inequality that we see, I don't really know. That's tough. There's good evidence in places like Scandinavia where significant work has been done. Not significant enough, but I'm not sure. Again, a lot of these questions, if I may reiterate to the audience, a lot of these questions boil down to how do we fundamentally transform basically everything about our society? And there's no good answers to that, but they're good questions.
Thank you very much. Sorry, I misspoke. There are 1, 2, 3, 4, 5 more questions. I guess we still have time, Cristy, correct?
Yeah, for sure. If Martin feels comfortable, we can extend the meeting.
Okay, perfect. Yeah, the next question would be, how much difference will individual behavior change make without higher level policy changes?
Again, there's no easy answer to this. There's a popular answer to this that says it won't make any difference. Assuming that we're just kind of disconnected atoms in a box where if I do something different, nothing else changes. But that's never really a compelling answer to me, because we're not, isolated elements in a box. Individual behavior could do nothing on its own. The action itself is not big enough to really make change, but these things cascade, right? So again, let's use Greta Thunberg as an example. Her individual behavior had a ripple effect that then caused a whole bunch of stuff to happen, right? So I think the kind of individual behavior narrative won't achieve anything makes sense when we think about it from just what the contributions are. But again, we need leadership in things, and ideas have to start somewhere. The enormous caveat to this is, the really big caveat is that interests who are vested interests in not changing over time, your fossil fuel companies, your other big producers, really like the individual behavior narrative because it takes the onus off them, right? So I can continue, tearing down mountains to dig coal out while individuals are pressured into changing their straw consumption habits. So there's a complex interplay there. We need leadership. It arises from individuals, hopefully, but at the same time, that narrative feeds really well into other people whose interest is in doing nothing. So we have to walk a tightrope on that one.
Yeah, I just want to echo back to your comment about inertia in the political system, where making changes is really, really difficult.
Yeah.
Well, thank you for your answer. Moving on to next question. This is a question related to the slides. Where was North America on the unnumbered slide on the bottom of the chart showing different geographic regions? I think it was asked an hour ago, and it was on the first 4 slides that you shown.
Dig up my slides for a second. Where is North America on the... Oh, right, yes. That's interesting. I have to believe that North America is the part titled Western Offshoots. It's a very odd way of phrasing it, to be honest, but I've just quickly looked back at the graph and there's nowhere labeled North America. So I'm going to make my best guess and say it's the thing labeled Western Offshoots.
Okay.
So it's there. It explains the kind of trajectories, but it's a ludicrous name.
Great. Well, thank you. There's a new question coming in. The most effective way, maybe the only way, to make the necessary change is through many new technologies yet to be invented. But let us hope this will happen. I agree.
So this is the awkward place that one finds themselves in talks like this. And this is, again, back to the role of engineers. So let's put it this way. Someone once phrased negative emissions technologies, the things that'll suck the CO2 out of the atmosphere, as an unfair high stakes gamble with the future, right? If we imagine that we'll have a technology that solves everything coming down the road, our impetus for action now is slowed. But to me, the problem is so incredibly severe that we still need these technologies. We still need people to come up with them. We need new ones. It's just that we can't rely on them to save us. They're critically necessary, but they can't be a substitute for our own behavioral change. But also this was sort of directly addressed by Peter, in that if you just have, again, going back to those emissions graphs, the one where we have this rapid decline in emissions from some miracle technology in 2040 still doesn't really get it because we had all the emissions beforehand. So
the cumulative, yeah.
Yeah, it's the cumulative is the real problem. So we're reliant on technological breakthroughs, but they themselves, I do not think personally, I could be terribly wrong, will be sufficient. We need both.
Yeah, so this kind of relates to a question that was asked by our audience. There is carbon extraction available in most countries, so how can it ever be regulated? And continued question or continued comments by him is that I agree electrifying transport, but I differ to Elon. It should be pole and rail pole pods rather than moving the batteries, EVs.
So I'll defer to the engineers in the group on that one. The specifics of transport electrification are, let's say, above or beyond my pay grade. The negative emissions one is a bit curious because we have a great negative emissions technology in some sense, which is just trees. So some of negative emissions involves bioenergy, carbon capture and storage. The problem in these things is to the scale they might be necessary. So a lot of the scenarios in the IPCC modeling assumes a really gargantuan amount of negative emissions tech kicking in after 2050. But I remember when I looked at the numbers about a year ago, most of the ranges for how much we need from those things kind of maybe or maybe not exceed what might be possible. So we do have them, but again, the problem is a scale thing. We need lots and lots of negative emissions, like really ludicrous amounts of it. So I don't know.
But even with carbon extraction, I guess, technology, you are just storing carbon. Is there any other way to break it down into some other elements?
So the only one that I know of, and again, that I definitely defer to the engineers here now, is that I think you can actually sometimes hilariously use that carbon again in some sort of advanced oil recovery. But my basic knowledge is you're just storing it, but I'm not super knowledgeable about the actual specifics of much of that technology. The other thing to consider is they keep having also new direct air capture facilities you see placed around some kind of coal mines or fossil fuel production. Those are hilariously expensive, and it's a drop in the bucket at present to what the actual magnitude is necessary. So the technology, we literally have the technology to do it. Then the problem becomes scaling, which is a vicious problem of its own right.
Okay, I think we are at 8:45, but one last question. It will be really quick, I promise. Is info@cusp.ac.uk the email to email Martin Serres?
Oh, that's a great. No, my email is, gosh, if I can remember it, NSERS@uvic.ca.
uvic.ca. Okay.
It's my UVic email. So I'm happy to answer email questions. I've also been heroically looking for the FAO report in the background, and I still haven't found it.
I think, those questions are pretty sharp. Sorry, do we have one more minute to answer one question? This is the last question. I'm going to closing the poll after this. How many people have gold in their investment portfolio or even no? Would love to come off mic to speak to this and see Martin's quadrant slides again. Okay.
Can you repeat the question? I didn't quite understand it.
Do you want me to just to say it?
Oh, sure.
Can we?
Yeah. Yes, please.
Yeah, just I wanted to, we talk about individual actions and how many people have gold in their portfolios or even know if they do. And I wasn't sure if we could go back to, your quadrant slide that you had. And if you can't, I just sort of, people have to start thinking about what they're buying and vote with their money. And there is no social purpose to gold. We have mined 40 years of it. It's sitting in vaults. What humanity mines something and then puts it back underground for years, right? And we have enough mined already to supply the jewelry market and the electronic market for 40 years. So but yet most of the investment in mining right now is 70% of it is in gold when we need all these critical minerals for our net zero energy transition. So we could, anyways, that's sort of the area that I work in. And I just was wondering if, do people know if they have gold?
That's a really, I never thought about it that way, but what kind of activity is to dig it up and then store it again? That's a really wonderful point. But this doesn't ruffle any feathers, but we're the same creatures who will set our computers to solve really complex algorithms to mine Bitcoin powered by coal we just dug up. So we're not, we have some weird traits. But again,
individual behaviors are key.
It's true, but I mean, this is a question I certainly have no answer to. But where do individual behaviors come from, right? It's always the interplay between some sort of society macro scale effect reaching down to the individuals who then percolate back up. Enlightened people might know, but how do we get everyone to do it? It's always the key question.
Having more conversations like this, because you never thought about gold.
Yeah, no, it's a brilliant point. I literally never thought of it that way. Learn new things.
I'm just going to say, I put in terms of, I'm very hopeful for our political systems. If you look at the YouTube video about sortism, it's proven scientifically that randomly selected people do a better job than politicians. And that's the way the Greek, actually, the history of politics first started.
You get rid of a whole lot of terrible incentive structures if you do it that way.
Great. So I believe we exhausted all the questions. And we exhausted you, Martin.
Yeah, and the speaker.
Yeah, so Cristy, I'll leave this to you to close this up.
So I will express our greatest appreciation for Dr. Martin to join us as a guest speaker, and for your supervisor, Dr. Victor Peter. And we will upload the video recordings after this seminar in our YouTube channel. You could find our YouTube channel and subscribe to us. And our next seminar will happen next month on July 28th. I put the link to registration. So thanks, Dr. Martin, for sharing your slides. I put the Google Drive share folder link for your slides for our audiences. So thanks, everyone. And I suggest everyone to turn on your camera and take a picture together. Thanks for your participation here tonight. So don't feel shy.
So thanks everyone for listening, by the way.
Yeah. We know we have a lot of returning audiences.
Yeah, I saw some familiar names and faces.
And Marnie is the council member at PO. She supported us in a lot of seminars before. And thanks for a question at the end of the seminar. We saw a lot of chapter representatives and members across Ontario. So it seems that a lot of people feel shy tonight. So we just take picture at this time. 3, 2, 1, smile. Take a latter one. 3, 2, 1. Thanks so much, everyone. Have a good night. We will close the meeting in a few seconds. Louis.
Thank you, everyone.
Thank you.
Have a good night.
Thank you. Good night.
Good night.